I'd like to start my introduction by telling you a story that made me think a lot about the difference between these two research models. And it goes way back. The story starts anyway back when I was a fairly new teacher. So I was teaching junior high school and high school sciences, and I looked for every opportunity during the summer to try and earn extra money because my wife was at home with kids, and I, I was one teacher. And even though things economically were probably a little bit better back then, not by much. So I was always looking for opportunities. And when I first started teaching, there were a lot of programs that were offered to teachers that addressed how to integrate STEM into whatever it was they were teaching. And science teachers definitely had an advantage when they applied for these programs, and I was no exception. So I got accepted into this program that was, again, sponsored through some National Science Foundation grants. And I spent a summer working as an intern at a electronics manufacturing area of a company called Motorola that eventually got sold to some other companies. The manufacturing did, but I'm sure many of you have probably heard of that company. They still make some really important microprocessing chips. And where I worked was in the manufacturing of whatever chips that they were actually making. So I spent that summer just working on some projects with other scientists and engineers. And my main charge, or my main task, was to try and identify ways that real-world applications of science and engineering might be integrated into what I taught as a science teacher. And part of learning about that was learning more about what a scientist or engineer does in their job. And so I interviewed lots of scientists and lots of engineers as I worked on some small projects. And one of the questions that I asked a lot had to do with the application of mathematics in their job. Because one thing that I knew as a science teacher is that I was required to take a lot of rather complex math, at least it was for me, to get through my program. And I know, having engineers in the family, having siblings who became engineers and parents, that an engineering degree required a tremendous amount of more complex math in college. So I would ask about math and about some of the other skills that it took to be successful in their jobs. And almost unanimously, when asked about what skills are needed to be a successful scientist or a successful engineer in this organization, almost unanimously, the first thing that came up was you have to be a good communicator, both in speaking and in writing. And I can understand that because there were a lot of meetings. Every Monday started with meetings, and people on various teams and sub-teams had to communicate to other people on the larger group where they were at with things. So I knew that communication skills were important. The next thing that came up consistently were really, really constructive collaboration skills. Those were being able to successfully work on a team. So that came up regularly. And I would say the third category of skills that, again, came up regularly had to do with critical thinking skills. You have to be a good problem solver. It seemed as if all the projects that these engineers and scientists were working on involved solving some types of problems. And so those were the big three regularly, consistently. So then I would ask about content related stuff. Again, like math. What math do you actually use and apply. And again, almost exclusively, no matter which job or which engineer or scientist I was speaking of, the math that was applied in their work regularly was generally pretty basic kinds of math. Now, some of them were actually working on projects that involve programming some types of computer-based things, and the math involved in that was math that is applied during trying to successfully write programs. But again, the math wasn't a huge part of the job, except to say that they needed to learn complex math in order to make it through the programs that got them into the job in the first place. Now, a number of these scientists and engineers did make this connection regularly by saying, well, the math that I learned helped me become a better problem solver, and it helped me become a better critical thinker. And so that was an important kind of conception that they all had. Now, one thing I knew about being a graduate student in the area of learning, applied educational psychology, was that there's very little evidence that learning complicated skills in one domain, like mathematics, that they transfer to other domains of learning. And in this case, it would be a broad domain of learning, like critical thinking skills. And so the transfer of skills from one area to another is something that I used to think a lot about, and it was something that I was happy to study more about as I went through my graduate program, and then as a faculty member in higher education. And it always stuck with me that people in jobs that you would think used a lot of complicated math regularly, actually there was another skill set that was more important, and particularly when you regard math as one of the fundamental basics that must be learned by most students at a certain level by the time they leave the education system. So I began to consider ways that you might measure what impact math and especially complicated math skills would have in other areas of life, and how you might study that. So you could imagine that one thing you could do in a positivist approach would be to randomly assign some subjects to a certain math program that facilitated more complex math, and another group of subjects who weren't assigned to that. And then at the end of the math learning experience, then the subjects would be tested on their critical thinking skills. So, and that's actually been done. Those are some studies that have been done. And again, the results of studies like that support more the idea that skills like that don't apply directly, to one other domain. Now, another thing that you could do, again related to a quantitative or positivist approach, is to try and imagine what kind of correlation you might expect if people who have more advanced math skills, that they would demonstrate more problem solving in other aspects of their life compared to people who don't have those. So, for example, and again, this is a bit of a stretch, but I'm just considering brainstorming. Having a successful relationship, once you get married or once you get into adulthood and many people get married, being able to successfully be married for an extended period of time requires a lot of problem solving. Now that I think about it, it also requires communication, collaboration, and critical thinking or problem solving skills, because not being able to solve problems in a relationship, you could make the assumption that might lead to the success, to the relationship not succeeding ultimately. So with those sort of ideas in mind, you might consider that that people who have learned more math in their life would actually have more successful relationships as adults. Now, I can attest in my own life, since I had a father who was an engineer, and I have a brother who's an engineer, and I have other people in my life who I know and love who are engineers, their success in relationships is no different, as far as I could tell, than people who don't have that math. And I bet a lot of people married to engineers would probably agree with that statement. I'm not sure, but I'm going to go out on a limb and say probably. So that would be one way to test that empirically, or through a correlation, where you could sort of categorize levels of math and categorize success in relationships and correlate those two. But there are other ways that you might study the value of learning complex math, being in education programs where you learn complex math. There might be other ways to measure the impact that might have on aspects of life outside of school. And so if you think about it, how might that look, or what might that look like? And I think one thing that you could do would be to find some subjects, or maybe a single subject, who did enjoy math and was successful in school with it, and sit down with them, have them communicate to you what that experience meant to them in their job and in their worldview, in their life. That, to me, the results of something like that might really provide some insight into the real impact of the kinds of fundamental skills that we value in education, and what that might look like as it transfers to the real life of people. So if that were the case, obviously you would need a research design or a research model that was not, grounded in a positivist approach. It would need to be grounded in something like an ethnography, where you, as the researcher, were immersing yourself in the life of somebody, and you were trying to focus your attention on things that they might say and do, and decisions that they may or may not have made in their life that were connected to the variables of interest that you were studying. And I thought a lot about that because I will tell you that many of the scientists and engineers that I got to know in my internship, both in that one, and I did something similar a few years later for Intel Corporation, there was a tremendous value for math and complex math for the people in those positions. And I think if I was going to study what the learning of that math, what impact it did have on their life, in their job and outside, I think I would, if I got under the hood of that, I think I might discover some really important things. And some of the things that I might discover could actually be incredibly valuable for educators, because it might be something that math educators especially might be able to use to help them contextualize math for their students and to create experiences that provided a degree of relevancy to learning complex math that they might not otherwise address. And certainly the statement, why do we have to learn this, when you get to certain aspects of math, that's an important question that learners need answered. So that's what this week is all about. It's about looking at other ways to study your variables of interest that don't involve more positivist approaches. And so there are three fundamental outcomes that you are going to need to learn and to be tested over, that all have to do with qualitative or or interpretivist models in general, and then also the specifics of different kinds of models that are in that category, and how they might be useful in order to successfully address your variables of interest that you might study. So I hope you enjoy part 3 of the class, and as well as the project that has you look at some qualitative research approaches.